So it's a pleasure to be here. Thank you for the invitation. So I will continue discussing on Bragg coherent X-ray imaging today and apply to catalysis. So catalysis is everywhere in our lives. It's about 90% of chemical manufacturing processes, and it has an important role in fields like energy, environment, agriculture, healthcare. So now it's quite well understood that the structure, meaning the defects, crystallinity, and strain, can be a key for the performance of a nanocatalyst, meaning the activity, selectivity, and reusability. Here I show you an example during oxygen reduction reaction. So they have a core shell nanostructure. So they succeeded to strain the shell. So here is the electrochemical activity. So they created a tension in the shell, and this decreased the electrochemical activity by 40%. Then by compressing the shell, this boosted the activity by 90%. So now it's quite well understood that the structure can be a key for the performance of nanocatalysts, but there are still some challenges, which are to resolve the structure in real environment at relevant scale and to develop predictive models. So for this, we need a technique which is sensitive to the structure, to strain, and the technique is Bragg coherent diffraction imaging. So we need a small beam, the size of a particle, with a coherent illumination. With X-rays, it's very nice because it can be applied in situ, operando, in complex, active, liquid, gas environments. And what we get, it's a dynamical structural imaging at the nanoscale. So how does it work? But there is a very nice talk of Ross. So we have our particle. We will measure a Bragg peak of this particle. Here I show you the 111 Bragg reflection. So the time of the measure is about 5 minutes compared to tomography or CDI in transmission. Here we are just rocking the sample by about 2 degrees. And we are measuring the intensity, so we are losing the phase. So we need to apply phase retrieval algorithms in order to get back the object. So the amplitude will give us the electron density, so it will give us the shape of the particle. And what is very interesting, as we are working in Bragg conditions, so in diffraction, the phase encodes the lattice displacement. Here is the lattice displacement, it's in picometer, and here the color scale is this lattice displacement. So here you can see, so the top and corners and edges are in blue, meaning in compression, compared to the facets, which are in tension. And this can modify the absorption energies of the reactants. So here is the size of our voxel for the reconstruction. The technique is also very sensitive to defects. So in few words, this is a 3D technique with a spatial resolution of about 5 to 10 nanometers, some strength sensitivity as we are working Bragg condition in diffraction to a few 10 to a 4, and we have some lattice displacement sensitivity of few picometers. So can we trust the technique? So can we trust the BCDI results? So as we are doing phase retrieval, so we don't have the atomic resolution. We have a resolution of 5 or 10 nanometers, but we know the support from phase retrieval. So by using, for instance, the nanoscope software, we can fill with atoms here the support. We can do atomistic relaxation and then get the displacement and the strain. And then we can compare it with experiments. And here it was the work of Maxime. So here it's what we obtained experimentally. So it's a platinum particle. We can see a lot of facets there. So then we can use the same shape of particle and do molecular static simulation. We need to use the same voxel size for the comparison. But for sure here in the simulation, the particle size is smaller compared to the experiment because we can't get the same size with a simulation. So we have the out-of-plane strain, and what we get is a very good comparison between experiment and molecular static simulations. So meaning that we can trust the technique to be surface sensitive to see what we are doing during catalysis. So the technique, the time measurement is quite fast, so we can measure different types of particles. So we are looking at platinum particles because they are good catalysts. So generally we have some perfect particles. sometimes we can see a defect. Sometimes here it's a twinned platinum particle, and here it's a twinned platinum particle with a defect. So for material scientists, it was quite impressive, to see some twinned platinum particle, because twinning is very rare in bulk. So twinning is very rare in bulk because platinum has a very high twin boundary energy. But at the nanoscale, we can see a lot of twinning and twinning platinum particles. Here I show you the diffraction pattern on our detectors, and you can see here that we have some gaps, because it's the technology of our detectors. So we just need to be careful when we have here this gap, because we can't impose the intensity, and sometimes it doesn't converge correctly. The intensity is not correct in the gaps. So we are doing interpolation to make it better, but if you have ideas how to improve this, it will be nice. Second point, so the technique is very sensitive to defects, so we can see defect in 3D. Here I show you a dislocation loop in a platinum particle. So we can get it also from the phase. So here we can see, so it's a cut of the phase, and we can see here some vortices. And the phase vortices, they have the signature of defects. And when we have a 2 pi, in fact, phase shift, here we have a 2 pi phase shift, we know that we have a displacement of 1 d spacing. Just to tell you that sometimes when we are working with defects, so we are using 3D phase unwrapping, and it doesn't work all the time. So I thought it can be a good idea to work on this field here. But okay, most of the time phase unwrapping works, so we can get the strain around the different segments of the dislocation. And here again, it was quite interesting because it's a platinum particle. And what we observe is that one segment of the dislocation lies in a 110 plane. And we measure another particle, it's a platinum particle, and the dislocation also lies in a 110 plane. And for a material scientist, in fact, 110 glide plane is very unusual. In FCC material, generally we have 111 glide plane. So this is the case for bulk, but here we are at the nanoscale, and we think that we have this unusual glide plane due to preferential surface nucleation. So we want now to measure quite fast. So we developed on-the-fly continuous Bragg coherent diffraction imaging. So by measuring continuously, we can go faster. We are increasing our speed of about 30% to do the measurements. And as we discussed before, now we can not only measure one reflection, but we can also measure several reflections. So here we measure 4 reflections on a nickel particle. And what is very interesting, so when we measure 3 non-collinear reflections, it's then possible to get the full 3D strain tensor of the particle and to get the 3D atomic displacement. So we can do it as a function of temperature, as a function of gas. This can be applied in situ. So we have done a simulation of a particle, so with a smaller size. Here it's the out-of-plane displacement, a strain that we get, and it compares well with what we obtain experimentally. So I show you a lot of ex situ results. So now we want to do operando in situ catalysis. So we want to understand and engineer structure of materials at atomic scale. So what we want as catalysis is quite complex. So we want to get the structure, the strain defect at the same time as activity, and to develop some predictive models. So for this, we need to develop some tools, some sample environments for catalysis. So we have developed a gas reactor that is compatible with nanobeam. It can go up to 950 degrees. We can flow gases. it should be very stable, so it's 3D printed and water cooled. And we have here a gas panel to flow the gases, and we have also a mass spectrometer. So we are doing experiments in gas, also doing electrochemistry. So with our collaboration at TU Eindhoven, we have developed an electrochemical cell, and we are also doing experiments during battery cycling. So we have also a battery cell. So all these equipments, they are compatible with nanofocus X-ray beams. So here now I want to show you some results, so what we can get during a reaction. So we look at the CO oxidation reaction, which is occurring in car exhaust. And okay, so we have again our platinum particle. So we will measure our platinum particle. We have the gas reactor here. So we have to work at 450 degrees to activate the reaction. We are flowing gases. So here you can see some reconstructions of the particle at 450 degrees and with different gas mixtures. What was first quite interesting, maybe I don't know if it's easy to see, but at the beginning we have like a roundish cheese particle, and then when we were flowing some oxygen, we can see some small facet formation. So we have facet formation, diffusion, material transport during the reaction. And if we compare with a work which has been done with transmission electron microscopy, we can see, so what they observe is that when we are in a CO-poor, CO-rich environment, so like here, CO-rich environment, they observe some round particle like us. And in a CO-poor environment, so when we are flowing oxygen, they observe some faceted particles. So we also observe some faceting as they can observe in transmission electron microscopy, but here it's with bigger particles. So we can also not only get the morphology, but we can also get the strain. So I won't say anything about the strain. And we have also the mass spectrometer connected to the reactor. So we have access to the CO2, so when the reaction is occurring. So we know when we are forming CO2 during the reaction. Another interesting thing here during the reaction, so we know that we have a defective particle. And here, if we look at the morphology of our particle, and as a function of gas, we can see that it evolves. So it's evolving with gas. So we have a change of the size of the crystal with gas. And in fact, what we have is twinned particle. So what does it mean? So it means that we have one portion of the crystal which has a 1-1-1 orientation. Then we have a sigma-3 twin boundary here. And the other portion of the crystal has another orientation. So we are not measuring it. So we are only measuring the grain with the 1-1-1 orientation. So we can see some twin boundary migration during the reaction. So when we are flowing CO, we can see that the twin boundary is moving in this direction, again here. So it was quite interesting to see some defect movement during a chemical gas reaction. This has been observed during indentation as a function of temperature. Here we are at a constant temperature. So we think that we have a chemical driving force for this twin boundary migration. So now I want to look more at the surface of the particle, how the strain evolves at the surface of the particle. So there was the upgrade of ESRF. So we went to Germany, to P10, to do the experiment. So we brought all our equipment there with the small reactor, the gas panel, everything. And now we will look at faceted particles and look how the strain at the surface can evolve during the reaction. So again, we are at 450 degrees because we need to activate the reaction. We are looking at one single reflection, 1-1-1. And here we are doing the reaction, so CO oxidation. And if you look at the diffraction pattern, we have a very big change of the diffraction pattern when we are doing the reaction. So we measure 3 different particles with different sizes and different facets. And so we need to index the different facets of a particle. So we can do this in reciprocal space because a facet is a 2D plane, so its Fourier transform is a 1D streak. So we can look at all these streaks there. But as we have our object in real space, so we can also do the facet indexation in real space. And we use the facet analyzer plugin of PowerView to do it. So then we can index all the different facets of a particle. Here I show you a table with for 2 particles, so a particle with a diameter of 300 nanometer and 650 nanometer. And it's all the facets that we observe. So we have some 111, 100, 110, 113 facets. So for the 300 particle facets, we have 32 facets, 43 facets for the particle with a diameter of 650 nanometers. So it's quite interesting because before, during catalysis, people were looking at surfaces, bulk with just one index. And here we have a nanoparticle with different types of facets, so we can see how they evolve as a function of reaction. So now we have the evolution of the displacement, lattice displacement, as a function of gas mixtures here. And we measure several times the particle. So here it's the first measurement, the last measurement with this gas condition. So the particle is still large, so it's 300 nanometer particle. So it's connected to a substrate. But first, what was quite interesting is that here we are looking at the bottom of the particle, and we can see some strong evolution of the strain at the bottom of the particle. We are not expecting this because there was this support, but this was interesting. And then when we are doing the reaction, so we are here, it's the CO oxidation, we can see a huge change of the strain on the surface of the particle. So we have some strain that builds up during the CO oxidation. So it was impressive to see how the particle can react during the reaction. But first, let's concentrate not on the reaction, but on oxygen adsorption and desorption, because we can flow oxygen. So generally, we start with a platinum particle. It's a metallic state. Then we oxidize the particle, and it was quite impressive to see a change of the strain here. So it's in the order of 10 to the minus 4. Yes. And then we have the oxidized particle. We will reduce the particle, and we are back to its metallic state. So we can do several cycles. So we have a metallic state of a particle. We are oxidizing and then reducing. And so we can see oxygen adsorption, desorption when we are flowing oxygen. So then it's very nice because we have all these type of facets, so we can see how they react during oxygen adsorption. And we just have to subtract the strain after oxidation and before. And what we observe is that the strain evolution is facet dependent. So we observe that all the 111 facets, in fact, they go into tension, so they go into positive strain, so they will turn in red here. And all the 100 and 113 facets, they tend to go into compression, so they will turn here in blue. And this is quite well known, so we know, in fact, there is this change of the strain because it's due to the different adsorption, and that oxygen will preferentially adsorbed on the 113 and 100 facets because they have lower coordination number, and we know that they have some initial tensile strain. And we have made, so it's Corentin who has made some DFT calculations, and what you observe, so we know our experimental strain. And we see that for 1,1 facets, in fact, the expected coverage for this strain, it's a very low coverage here, so around 0.2 monolayer. But for 1,00 facet, we expect a higher oxygen coverage. So it's confirmed by DFT calculations. So now, what about the reaction? So during the reaction, it's quite impressive. I mean, the displacement here will change a lot. So we will have a huge change of the displacement. But in this case, if we look at the 1,10 facet, they will not react on the same way. So some facets will go in tension, so plus positive, in compression, or they don't evolve. And it's the same thing for the 113 facets. So during the reaction, so what we have observed is that the HKL facets, they don't behave the same way, and that we have some larger strain variations on the facets which are close to the substrate. So here we have some huge variation, and we have a -1, -3, 1 facet, and this facet is, for instance, located here. So where we have a large strain is for the facets located close to the substrate. So what we have observed here is that strain evolution is facet dependent during oxygen adsorption and support dependent during the CO oxidation. So the metal-support interaction is very important for the performance in catalysis, and this will help to localize the active sites during the reaction. So now I want to move on the liquid experiment. So I show you some results on the gas experiment. So the electrochemists, they want to find the best electrocatalyst. So for this, it can depend on the crystallographic orientation, structural defects, strain, and ligand effects. So again, we will stay with platinum particles because they are benchmark catalysts for fuel cells and electrolyzer. And this is in the framework of the PhD phases of Clément. So here we have no gas, but we have an electrolyte. So we have sulfuric acid. And we will apply a potential, a CV curve, and what we obtain with our electrochemical cell is very comparable to what can be obtained in laboratory. So we were quite happy here. But we just look at the evolution of a platinum particle in this region. So this region is called the double layer region. And what we observe, so it's a platinum particle, and we observe how, so it's the strain, and we increase the potential, and we observe again a very huge change of the strain by applying a potential. So at the beginning, when we have, again, we have a faceted particle, so we can do DFT calculation just to compare the displacement of what we get experimentally by DFT, and it's quite impressive what we can get, because we hear the ratio, I mean, it's very small simulated particle, so we can get the pristine state, and it's just due to the morphology of the particle. And then by applying potential, maybe it's not so easy to see here, so here you have the color code, it's the strain, and the arrows there, it's the lattice displacement. And what we can see is that with potential, we have the strain and displacement that is evolving. For instance, we can concentrate here, so it's blue, it will become more and more blue and larger displacement. So here, just to concentrate, so we made just some histograms. So we wanted to look to see how the strain in the bulk and at the surface, how they evolve during the reaction as a function of potential. And what we observe is that for the bulk here, it's in orange, that we have some change of a histogram of the strain in the bulk. So they were not expecting this, that during electrochemistry, I mean in the double layer region, that the strain can propagate from the surface to the bulk of a nanoparticle. And for the surface, yes, we have some large changes. But for the surface, we can concentrate on facets and edges. So edges here and corners, they are in green, and we see that they are moving in the negative direction, so in compression, and the facets are going in the positive direction and in tension. And we know that we have some bisulfate adsorption in this region. So here, what we observe, we were able just to see in this double layer region the adsorption of ions that will be preferentially on the corner edges of the particle, and that the strain propagates from the surface to the bulk. So now, what we want to get is, it's a dream of everyone here, or at least in our field, is to get the ultimate Bragg X-ray microscope. So it's to go to atomic scale and real time. So we measure some large particle with a size of at least 100 nanometer, but Catalysis, it's more 10 nanometer. So we want to measure smaller particle and to do faster measurements. And in 2020, there was a upgrade of ESRF. And now we have an extremely brilliant source at ESRF. We have 40 more, it's an increase by 40 of the brilliance and coherence. So then the idea is to be more surface interface sensitive and to do some slow motion movie to see some different steps in chemistry and in physics. So what have we done with this new beam? So we have started to play with this new beam. So we have demonstrated that it's possible to measure particles as small as 20 nanometer. So this was quite interesting. Also, we can measure superstructural reflections. So we are more flux. So we can try to look at atomic ordering, for instance, with these superstructural reflections. And all the measurements that I show you and that people are showing you with Bragg current diffraction imaging are obtained at an energy of 8-10 keV. And now with more coherence and brilliance, we can go to higher energy. So we can go to 33 keV. We can measure particles with this energy. So with at higher energy, we have higher X-ray penetration. We can look at embedded grains in polycrystals, and we have less beam damage. So we have seen that it works better to work at 33 keV at higher energy for electrochemistry. Just to show you that it's possible to make some measurement at 33.4 keV with the new beam, and we have the same quality for the particles. So we have our test particle. Here, what was quite funny at the beginning, so we have our test particle. Here, we did the measurement at 3 energies. So close to 20 keV, 33.4, 8.5 keV. So the shape is the same, but the phase and the strain is totally different. And we were not expecting this. And in fact, it's a test sample, and we are measuring in air with this test sample. So at the end of the experiment, we have performed some scanning electron microscopy, and we have seen a lot of carbon contamination on the sample, and this explains this different strain. So what is also nice when we go to higher energy is that we can reach reflections that were unreachable at 8.5 keV. So generally, we are looking at low-order reflection, but at higher energy, so the reciprocal space is increased, and we can measure some high-order reflection, like the 5-33 reflection, and these high-order reflections are more strain-sensitive. So it will be very interesting to look at this high-order reflection, and it works for these energies. So then, when we are doing some in situ operando Bragg current diffraction imaging, we want to do the data treatment very fast online. So for this, David, with a PhD student in the group, has developed a graphical unit interface, based on the Jupyter notebook. So what it's doing, it's doing just on one notebook, we can do the pre-processing, the phase retrieval, and the post-processing. So it's going very fast, and we are trying to do some online analysis and everything. So all the pre-processing part, post-processing, and phase retrieval, yes, they are in the same notebook. And also what is very important for us is the reproducibility of the data. And so at the end, what we have, it's just one file, one H5 file with all the data and parameters that have been used for the pre-processing, phase retrieval, and post-processing. So someone can redo the analysis and compare and retry or compare the different parameters. So it is GitHub. So then another thing, here we are discussing a lot about machine learning, and we are also going the direction of machine learning. So we are trying in two directions. So we want also to replace phase retrieval by machine learning, but we are making some small tests. But also we are thinking about also classification. So there are some limits of phase retrieval when we are working in Bragg coherent diffraction imaging, is that phase retrieval does not always converge, and this is the case of highly strained nanoparticles or particles with defect. So then the idea was, okay, if we want to do some classification for particles with defect, we have just to stay in the Fourier space. So in fact, when we have defects, so here it's a perfect edge defect or dissociated edge defect. If we look at the diffraction pattern, we will see some features. So we know that defects have a very defined signature in a Fourier space. So we say, why not developing a convolutional neural network for defect recognition from 3D diffraction patterns. So when we are at the beamline, we look very fast if there is a defect, if it's a perfect particle, and to have some machine learning that can help us in this way. So the big trick here, so yes, the question is, can machine learning help us to screen particles and detect defects? So the big part of the process is to build the data sets and to have the data sets very close to reality. So we look at some dislocations, so edge or screw dislocations. So to make this very close, the data set very close to reality, so we use the Merlin software. It allows to create a single defect with atomistic configuration. Then we need to relax the atomistic, to do atomistic relaxation to be closer to the physics. And then we need, after this, to calculate the 3D diffraction pattern and then to train the data. So with this, we have created 100,000 data sets. So here it's the neural network. So the input is the 3D coherent diffraction pattern. The output will be the probability of the three classes. So either there is no defect in the particle, there is a screw or edge dislocation. So I told you that for the simulated data, so it's here the number that we needed for the diffraction patterns. We have done the training with ADAM optimization, a learning rate of 0.001 and batch size, which is 64. And what we get here, it's a total accuracy score on the test set of 97.2%. We have also performed the confusion matrix to see how it works well or not. So it works quite well to detect a perfect crystal and a little less when we are working when there is an edge dislocation. So we have a 3D coherent diffraction pattern. So we have experimental data. And also we can do phase retrieval, so we know if there is in this experimental data. With phase retrieval, we know if there is a defect or not. So here there's no defect. Here we know that there is a screw dislocation. So we know the nature that it's a screw dislocation because we have atomic displacement. So we know how the phase is varying around the defect. And so we apply the neural network. And in fact, we obtain each time, so maybe not for the first case, but each time a correct identification. I mean, here it's a correct identification, but maybe quite low. Here it was very good to determine that it's a screw dislocation, quite good that it's a perfect crystal, and here quite good that it's a screw dislocation. So this neural network, we are quite happy, so it works on experimental data, so it's on one D defect. So now we are playing with 2D planar defects, and it seems to work also quite well. So yes, then we are working to approach the atomic resolution with our new X-ray beam. So I won't tell you a lot of things. Just to tell you that with the new X-ray beam, now we can measure quite far in reciprocal space. Here, with the extent that we are measuring, we expect a resolution of about 1 nanometer. So we are working in this field. Just to tell you that now the BCDI approximations, they stop, they're invalid. The phase is no more doesn't encode no more, the atomic displacement, and the Eva sphere curvature is not negligible. So on this, I want to acknowledge the team, the PhD students, the postdocs, the ID1 beamline we're working at, and with Steven and my colleagues and collaborators. Yes, we are looking for a postdoc for doing nanoimaging with deep neural networks. And thank you for your attention.